Hi, I'm Tim the Techno-Gardener, and this is the first video in a multi-part series where I attempt to build 3D printed solar-powered micro greenhouses that can grow plants outdoors even in winter. In this first video, we'll build a prototype, test how well it retains heat, and calculate its R factor. I live in Utah where the growing season is short, typically from late May to the end of September. That's only about 4.5 months. And even then, the weather is unpredictable. It can be 80 degrees in May, and then a hailstorm in June can wipe everything out. So you may ask, why not just build a traditional greenhouse? My first answer is, that's boring. The goal of this channel is to push the boundaries of agricultural technology to explore new ideas and better approaches. Traditional greenhouses are designed for people, not plants. They're tall, they have doors, and they include walkways so humans can move around inside. But plants don't need that. A greenhouse designed purely for plants could be just tall enough for the plant itself, with openings only large enough to access it. Because traditional greenhouses are human-sized, they have far more surface area than necessary, and that extra surface area leads to heat loss. Larger internal volumes also require more heating. In other words, they waste energy. Heat loss scales with surface area. If you can reduce the surface area dramatically, you can reduce the required heating power by the same factor. A greenhouse with 1/100th of the surface area could in theory require 1/100th of the energy. Greenhouse materials are rated by R factor. The higher the value, the better the insulation. Double-walled polycarbonate has an R value around 1 to 2. Triple wall is about 2 to 3. Even 5-wall polycarbonate panels don't get much higher, and each additional wall reduces light transmission and increases cost. For comparison, fiberglass insulation is around R4 per inch. So for these micro greenhouses, our goal is to maximize insulation while allowing enough light for plant growth. Some larger systems use climate batteries bearing tubing deep underground to store heat in the soil. These systems can stabilize temperature, but they're complex, expensive, and still need backup heating during extended cold periods. So instead of scaling up, we're going to scale down. The idea is simple, a greenhouse sized for a single plant. I'm designing a 3D printed insulated cylinder that sits in the ground with a transparent insulated lid tall enough to accommodate the plant's growth. The bottom remains open but is thermally buffered from the surrounding soil using mulch or perlite. Once the cold season passes, the cylinder can be removed without disturbing the roots, allowing the plant to continually grow naturally. For my initial testing, I already know that passive heating won't be enough. So I'm also developing waterproof heating cartridges that can run on solar or line power. These will be placed below the root zone using the soil itself as a thermal battery. During the day, the soil stores heat. At night, it releases that heat back into the air, helping stabilize the temperature around the plant. I want to approach this as an engineer, designing, measuring, and validating each parameter. Some of the key questions we'll explore are, what's the best R factor we can achieve with 3D printing? Can we maintain sufficient light transmission? How much soil mass is needed for thermal stability? How does soil moisture affect heat capacity? What's the optimal heater power? How hot should the soil get? And how long can the system maintain temperature overnight? And I'm sure we'll run into other problems we haven't even thought of yet. All right, let's get started. I've already built a first test chamber to measure the R factor of a 3D printed wall. The final micro greenhouse will have a window to let light in. The sole purpose of this chamber is to calculate the R factor of the 3D printed walls. It's a cylinder, 190 millimeters in diameter, 200 millimeters long with a wall thickness of 25 millimeters, or about 1 inch. These dimensions are close to the maximum size my 3D printer can handle. We want to minimize surface area to volume, and without getting into the calculus, that happens when the height is roughly equal to the diameter. So this geometry is close to optimal. The chamber is printed in 3 parts, a hollow tube and 2 end caps. The top cap has 2 holes, one for the heater wires and one for a temperature sensor. For this first test, the walls are hollow, just air inside. In future iterations, we'll experiment with different insulating materials. The final design will include a transparent lid, but this setup will give us a good baseline. I'm using Vegetronics Therm 200 sensors to measure both internal and ambient temperature. These are connected to a VeggieHub data logger, which uploads the data to veggiecloud.com for visualization. The heater is very simple. A 75 ohm resistor powered at 12.3 volts, producing about 2 watts of heat. Everything is sealed with masking tape. Let's turn it on and collect some data. By the way, I'm Tim, an electrical engineer who applies engineering principles to gardening. If that interests you, consider subscribing. This system behaves a lot like an electrical circuit. The insulation acts like a resistor, and the thermal mass acts like a capacitor. Heat flows out over time, just like charge dissipating through a resistor. This experiment has been running for about an hour, and the temperature in the chamber has reached equilibrium. The inside temperature is no longer increasing. The next step is to look at our data and find out what the temperature difference is so we can calculate the R factor. I've brought up veggiecloud.com and graphed the inside and outside temperatures over time. You can see that at equilibrium, the temperature difference is about 10 degrees Fahrenheit. Since we know the power flowing into the chamber and the surface area of the chamber, we can calculate the R factor. Using this equation, where delta T is in Fahrenheit, A is area in square feet, and P is power in BTU per hour, we calculate an R factor of about 2.8. That's actually quite good, better than 5-wall polycarbonate and comparable to 1-inch thick fiberglass insulation. Now that we know the R factor, we can tweak the other parameters of our micro-greenhouse to optimize it. Next, let's look at how long the chamber retains heat. When the heater is turned off, the temperature decays exponentially toward the ambient temperature. The rate depends on both the R factor and the heat capacity of the system. From the data, we can estimate the time constant, or the time it takes to decay, by 63%. In this case, that's about 23 minutes. From the time constant, we can calculate the thermal mass of the system, which includes the chamber, heater, sensor, and wires. High thermal mass materials take a long time to change temperature, and low thermal mass materials change quickly. From a 23-minute time constant, we calculate a thermal mass of about 500 joules per Kelvin. For comparison, water has a heat capacity of over 4,000 joules per Kelvin, over 8 times higher. If the chamber were filled with water, the time constant would increase to around 3 hours, which is a third of what we need to get the plant through a cold night. So we may need to increase the power from the heater or increase the volume of the chamber. In reality, we'll be working with moist soil, not pure water, so we'll need to tweak the insulation, thermal mass, and heater power to lengthen the time constant. But this first test shows something important. This idea might actually work. In the next video, we'll test new designs to increase the R factor even further. If you have suggestions, leave them in the comments down below. And if you made it this far in the video, I guarantee that you'll enjoy my other videos, so you might as well subscribe and check out Vegetronics.com for more cool gardening gadgets and automation ideas.